Hello, everyone. Welcome back to Med Zone African Motives. We want to start on our revision for our end of year examinations, which are going to come. So we are going to be using question papers for October and November end of year. So what we are going to do is to look into paper 1 and paper 2 separately. So today I brought you a question paper from the Eastern Cape province. It was from the OR Inland Tambo district for grade 10 physical sciences, which was paper 1. So the question paper was written in October 2024 and it was housing 100 marks, which was supposed to be written in 2 hours. So today we want to see if we can help each other answer this question paper in 2 hours and also get to see what is it that was expected of us. So these are the instructions. Pay particular attention to instruction number 8. Show all formulae and substitutions in all calculations. So for you to get full marks, you were supposed to show all formulas and the substitution therefore. And then you are supposed to round off your numerical answers to a minimum of 2 decimal places. And then you were supposed to, for where questions requires a graph to be drawn, a graph paper was provided from this question paper. So always graph papers are provided and they come with question papers. So you need to pluck out that graph paper, you draw your graph paper and then attach it to your answer booklet. So let's learn to read and follow these instructions. They will help us and they will guide us in our writing. Now, question number 1, as usual, we'll be having multiple choice questions. And this question paper was having 6 multiple choice questions. And they were out of 12 marks, each question having 2 marks. And you are always given 4 options, which is option A, B, and C, as well as D. So you need to choose only one option. You only have one correct option, which is more accurate. Now, question number 1.1 was saying the amplitude taken, the time taken for one complete wave is known as. What is the time taken for one complete wave pulse? This is the period of the wave pulse. So this defines the period of the wave, where we know that period is the time taken for one complete wave. So our answer there was supposed to be C. Now let's go to question number 2, which is 1.2. So question number 1.2 was now saying that two sources A and B produce a transverse wave, and then source A produces a transverse wave having a frequency of 10 Hz. If source B produces 1000 waves in 20 seconds, its frequency would be, so the frequency of B, how can we calculate frequency? We can either say 1 over the time taken to complete one wave, or else we can say the number of waves completed divided the time it takes to complete those waves. So here we've got 1000 waves completed in 20 seconds. So we can have our frequency being equal to, if you divide 1000 by 20, you are going to get 50. So this is 50 waves completed in 1 second. So this corresponds to 50 Hertz. So frequency A, or else frequency of source A, it's 10 Hertz, whilst the frequency of source B would be 50 Hertz. Now they are saying option A, frequency of B is 8 times the frequency of A. This is wrong, because frequency of B is just what? 5 times the frequency of A. So 5 times the frequency of source A. So our answer was going to be B, where we are saying frequency of B is 5 times frequency of A. Because if you say 5 times 10, it will give you 50 Hertz. Let's go to question number 1.3. So question number 1.3 is saying oil is dripping from a truck at equal time intervals, leaving a pattern below, leaving a pattern that is drawn below. If the truck is moving eastward, Which one of the combinations below best describes the speed of the truck during the intervals M to Q, Q to V, and V to Z? So we want to describe the speed given, they say that given the intervals from M going to Q, how is the speed changing? From Q going to V, how is the speed changing? From V going to Z, how is the speed changing? So what helps us to describe our speed here is the frequency of our drops, or else the number of drops that we are getting within this distance. So you can see that the frequency is decreasing. How do we see that? We see that the gap here was longer than this, longer than that, longer than that. So the gap in between the drops is decreasing. So we can actually simply see that also here our speed corresponds to the frequency of what? To the frequency of our drops. The more the number of drops that we have within a short time of period, the lower the speed. So here we can see that we are increasing in the frequency. So here we can say that our speed is decreasing. And then here we can see that the number of drops, or else the frequency, remains the same. So our speed also what? Remains constant. And then here you can see that the gap here was shorter. It is now increasing, increasing, increasing. So we can see that the frequency is decreasing of our oil drops. So we can say that the speed here is what? Is increasing. So we are looking for an answer that says decrease from M to Q. So we are decreasing from M to Q, and then remain the same from Q to what? To V, and then increase from V to Z. So our option was going to be C. Now let's go to the following, which is question number 1.4. Question number 1.4 is saying an object traveling with a speed of V has a kinetic energy E. What will be the kinetic energy in terms of E if the speed is increased to 4V? So when we were having our speed being equal to V, the kinetic energy would be given by half mv squared. What about when now we are now given that the speed is now 4 times? So it will be 4v squared. So this corresponds to half times our m. 4 squared becomes 16, v squared becomes v squared. So you can see that I'm having 16 times a half of mv squared. So this corresponds to E. So I'm having 16E. So whenever we are increasing our speed, it simply means that our kinetic energy is also going to increase. So the factor there will determine. So here we increased to 4v, so it will be 4 squared. So it becomes 16E. Now we are saying a rod acquires a positive charge after it was rubbed with a cloth during the process. So we are having a rod. Usually this is neutral. So let me just get to rub here, and then I will illustrate on top. So here is our rod, which is neutrally charged. I'll represent the charges with positive, and then positive, and then positive. And then we are having negative and negative. So at some point in time, I was also supposed to. So here I've got a positive. So I'll need to have a negative there. So this is our rod, which is what? Neutrally charged. You can see it has got 3 negatives, 3 positives. And then after charging, after, the rod is now said to be having what? It is now said to be positively charged. So it is only remaining with what? With the positive charges. So it simply means that we have transferred these negative charges to whatsoever is what is rubbing our rod. So this being the rod, we are transferring the negative charge to the what? To the cloth. And usually the negative charge actually represents what? It represents electrons. So we are saying that electrons are being transferred to the what? To the cloth from the rod. Now let's see the options that are given. So they are saying during the process, A, electrons were transferred from the cloth to the rod. This is incorrect. B, electrons were transferred from the rod to the cloth. This is actually correct. So our answer is B, because when something was neutral and then it now comes to be positively charged after charging, it simply means that we have transferred, or else we have lost the negative charges. So we have lost the electrons. So the electrons were transferred from the rod itself to the what? To the cloth that was charging it. Now 1.6 is saying 1 joule per coulomb of charge, 1 joule per coulomb of what? Of charge is. What does 1 joule per coulomb of charge represent? We can say that 1 joule per coulomb of charge, joules represents what? Energy. So energy can be transferred. So it's energy transferred, or else energy dissipated. And then coulombs represents what? Charge. So what is defined, or else what does energy transferred per unit charge represent? This represents what? Potential difference. We know that potential difference is the energy transferred per unit charge. And potential difference is measured, or else it is given in volts. And volts, it's V. So 1 joule per unit coulomb would be equivalent to 1 volt. So our answer is supposed to be 1 volt, which is corresponding to what? To C. So our answer there was C. So that was it for our multiple choice questions. That was out of 12 marks. Now let's start on question number 2, which is our structured questions. 2 transverse pulses, which is X and Y, are moving at the same speed at the same time along a light string. So they're saying pulse X is moving towards the right, as you can see from the diagram, and pulse Y is moving towards the left, as it can be shown there. And they're saying that the amplitude of X is positive 5 centimeters, and then amplitude of Y, it's negative 8. And then pulses X and Y, they meet at Z. So there is some interference at Z. Assume that all energy is conserved. So if all energy is conserved, it simply means that the amplitude of X will remain the same after the interference. And then the amplitude of Y as well will remain the same after the interference. But however, let's look at interference before we can start answering the questions. When it comes to interference, we have got 2 types of interferences. There is constructive interference. So constructive interference is when 2 pulses meet and there is increased what? There is increased amplitude. Whenever 2 pulses meet and there is increased amplitude, you know that you have got what? Constructive interference. And then where you have got destructive interference, this is when you have 2 pulses meeting and then the amplitude is decreased. So whenever you have got decreased amplitude being the result of 2 wave pulses meeting, it simply means that it is what? There is destructive interference. In diagram, you know that you can have this, the pulse going to the right, whilst you have got a pulse that is also going to the left. If these 2 meet, they are going to have an increased amplitude. What do we mean by that? We are saying that we are going to be able to add the total displacement of the particles within these wave pulses would be summative to the displacement of the two what? Of the two pulses. So it will be equal to the what? To the two sums, or else to the sum of these two. But when it comes to this side, let's say the other one is a positive in this format, and then the other one, it's a negative in that format. What is going to happen is we are going to have what we refer to as what? As a destructive interference, where we are going to subtract the two. So at the end of the day, you might have something like that. It means that our particles will not be disturbed, or else they won't be displaced from the what? From the wave itself, or else the amplitude is just going to decrease. We might have a decrease that might be in the negative, or else in the positive. So whenever we've got a positive and a negative pulse meeting, they form a destructive. But whenever we've got a positive and a positive, or else we've got a negative and a negative, where the other one is this side and it's going that side, and then the other one is also the same side but going that side, these two, they can be summed and they have a bigger what? A bigger negative, which simply represent a what? A longer amplitude. So that is how you define, or else that is how we can remember destructive interference and what? And constructive interference. Now from the given information, let's hear what the questions are saying. What type of interference will take place when these two pulses meet at Z? We've got a positive pulse and a negative pulse, or else we've got a pulse that is carrying a positive amplitude and the one that is carrying a negative amplitude. Simply this would be what? Destructive. So this would result in a destructive what? Interference. So the answer there was what? Destructive interference. Now, the following is now saying, make a labeled sketch to represent these two pulses when they meet. So we've already shown examples of how some that look similar to this would actually get to interact. So these ones, when they interact, since we are having positive side 5 that side, and then we would be having what? Negative 8. So when they meet, this is what is going to happen. So you are going to be able to add positive 5 centimeters and negative 8 centimeters. These two will give you what? They will give you negative 3 centimeters. So the resulting amplitude would be in the negative direction, and it would be negative 3. So that is what you are just supposed to draw there. So you were supposed to indicate this amplitude, that it will now be equal to what? Negative 3 centimeters. So given 2 marks, the first mark would be on the shape, which is the diagram of the interference result. And then the second mark would be on the correct what? Mark of the amplitude and its representation. Now they are saying, how will the amplitude of Y change after the interference with pulse X? They said, assume that all energy is conserved. So we are saying that the energy of Y would be conserved. Hence, therefore, its amplitude would remain the same. So the answer there, you are just supposed to choose what? Stays the same. Now let's go to 2.2. 2.2 is saying a certain transverse wave travels at a speed of 0.4 meters per second. So this is the speed of the wave. The distance between the 7 consecutive crests on the same wave is 12 centimeters. And they are now saying, define the term wavelength of a wave. What is the wavelength of a wave? This is the distance between 2 consecutive or successive points that are in phase. This is the distance between 2 successive points, in phase. 2 successive points in phase. That's the reason why here we are given what? 7 consecutive crests. So let me just get to draw that so that we can be able to answer the following questions. I'm sure it has to do with those 7 consecutive what? Crests. So 7 consecutive crests would look like this. I would be having 1. Let me just try to save space there. I would be having 1, 2, 3. Don't mind my diagram there. I'm just trying to represent the wave. So we have got 1, 2, 3, 4, 5, 6, and 7 crests. I managed to do that. So we have 1, 2, 3, 4, 5, 6, 7 crests. And they're saying that the distance between those 7 crests is equivalent to what? To 12 centimeters. And then now they're saying, determine the wavelength of the wave. We know that the wavelength is the distance between 2 consecutive crests. That is the wavelength. So here, how many consecutive how many wavelengths do we have? We can actually get to calculate to say 1, 2, 3, 4, and then the other one will be here, 5, the other one will be here, 6. So we have got 6 wavelengths. And those 6 wavelengths, they are equal to what? To 12 centimeters. What would be equivalent to 1 wavelength? That is the distance that you are looking for. So you can say 1 wavelength divided by what? By 12 wavelengths times 12 centimeters. So that these wavelengths, they can cancel each other. So here I was supposed to say over 6. Sorry. So it's 1 wavelength divided by 6 wavelengths that are there in 7 crests. And then you multiply by 12 centimeters. And then these ones cancel out. You'll be left with 12 centimeters divided by 6. So 1 wavelength would be equal to 12 divided by 6. That is 2 centimeters. But they say the answer should be in meters. So you know that 1 meter is equal to 100 centimeters. So we come here and then we divide by what? By 100 centimeters. So 1 wavelength would be equal to what? It would be equal to 0.02 meters. That was the answer that you were supposed to write there. So just allow me to wrap this because we've seen how we calculate that. So now we are saying that each wavelength is equal to 0.02 meters. Now they are saying calculate the frequency of the wave. This is when we apply what we refer to as the wave equation, where we say speed of a wave is given by the frequency of that wave times its wavelength. Here we've got the speed that was given, so we're given the speed of this wave. So the speed of this wave here, it was mentioned as 0.4. So we have got 0.4 meters per second being equal to the frequency times the wavelength that we have just calculated, which is 0.02. So the frequency there would be equal to 0.4 divided by 0.02. So you would find out that the frequency of the wave would be equal to what? If you look for that, if you punch your calculators, I'm sure you would be able to calculate and find what? 20 hertz. That is the frequency there. So you were just supposed to apply the wave equation. Now they're saying that a sound wave moves along a slinky spring, and position A and B are the centers of a compression and a rarefaction, respectively. A and B are 24 centimeters apart. Are A and B points in phase, right? Yes or no? So we want to know, how do you determine points that are in phase? Points that are in phase are when you have, because this one is a longitudinal wave. When you have a longitudinal wave, it's either the center of the crest as well as the center of the crest, or else the center of the rarefaction, or else the center of the rarefaction. these 2 points, they are in phase. But when you see the center of the crest, the center of the compression and then the center of the rarefaction, it simply means that they are not in phase. If we were having a transverse wave, we would be looking for crest, crest, or else trough, trough. So these ones would be what? Your crests. And then these ones will be your troughs. Those are the only points, or else you'll be looking for this point as well as that point. Points that are successive are the ones that are actually what? In phase. So you can see that by the given information, we have got a rarefaction as well as a what? As a compression. So you would actually get to come here and say, no, these 2 points, they are not in phase. Why? Because A is the center of a compression and B is the center of the rarefaction. Only a compression and a compression can be in phase, or else a rarefaction and a rarefaction. So let me just get you write this down. So this is where we are calculating our what? Our wavelength. So let me just get to. So we are saying that no, because A is a center of a compression and B is a center of a rarefaction. This information was already given. You could have just came and said only the center of either a compression and a compression or a rarefaction and a rarefaction would be in phase, can be in phase. So that is what we're just supposed to write there. That no points A and B, they are not in phase. Why? Because A is the center of a compression and this one of a rarefaction. Only the two centers of what? Of two successive or consecutive what? Consecutive compressions can be in what? In phase. Now let's hear what the next question is saying. They are now saying, determine the period of the wave if it takes 5 seconds for a particle to move from point A to point B. Let's return to our wave. So on our wave then, we have got point A and point B. And we need to determine either the wavelength, the frequency, or the distance in between. The distance is 24 centimeters. How would you determine its wavelength? You know that a wavelength would be the distance between a center of the compression and another compression, or else this compression and another compression, or else that compression and another compression. But here we see that we have got two wavelengths, and then we have got a half wavelength. So here we have got 2.5 by a wavelength, which is equal to what? To 24 centimeters. So between points A and B, there are 2.5 wavelengths. And then they are saying that it takes 5 seconds to move from point A to B. So it takes 5 seconds to move what? 2.5 wavelengths. So what becomes its what? Its period. So the period can be the time taken divided by the what? By the number of waves that passes through that time taken. So it will be 5 seconds divided by 2.5 waves. And this will give you 2 seconds. So we are saying that one complete wave takes 2 seconds, or else a particle takes 2 seconds to complete 1 wave, or else to actually move one complete wavelength. That is what we are saying. So the period there was just supposed to be equal to what? To 2 seconds. Now they are giving us a note of this sound wave with the same speed is played at a higher pitch than before. How does this affect the following? Write down increases, decreases, or remains the what? The same.